biggest critical infrastructures we have nowadays is power generation. If there's no power, we're pretty much screwed. Our next speakers will take a very close look at common industrial control systems used in power turbines and their shortcomings. So please give a warm round of applause to Reptep, Moradek, and Kors.
Good morning, Congress. Thank you for waking up in the morning. We will talk about the security of power plants today, specifically about automation systems that are used in the power plants. You might think that this is another talk about how insecure the whole industrial things around us are, and more or less it is. So for years we and our colleagues speak about problems in industrial security. We are happy to say that things are getting better, but it's just that the tempo is a little bit different and feels a little bit uncomfortable. So anyway, we will speak about like how power plants are built, what is the automation inside, what are the vulnerabilities, and like the high-level overview of what you can do with this. But at first, a little bit of introduction. We are security consultants. We work with a lot of industrial things like PLCs, RTUs, SCADAs, DCSs, whatever it is. We were doing this for too long. Actually for so long that we have a huge map of contacts with a lot of system integrators and vendors. And throughout the time, we are not just doing the consultancy work for some asset owner, for example, for a power plant. We also talk to other entities and we try to fix things all together. We work at Kaspersky, and actually the whole research was done not just by me, Rado, and Alexander, who are here, but also with the help of Evgenia and two Sergeys. So things that are very important to note is that everything that we will discuss right now is reported to a respective vendor, basically a long time ago. You can see like vendors here, but more or less we will speak only about one vendor today. It is Siemens, but we would like you to understand that similar security issues can be found in all other industrial solutions from other vendors. You would find some of the findings not, for example, that stellar, and it doesn't require like weeks of work to find them out. And this would be true specifically for all other vendors which are not mentioned in the talk. Jokes aside, we will share security issues of real power plants out there. And it might look like we are kind of irresponsible guys, but in fact, this is the other way around. I mean that to do some kind of research on with these systems that are working in the power plants, you need to get access to them, you need time to do this research, you need to have some knowledge to do this research. And all these resources, they are limited for guys like us, for penetration testers, for auditors, for power plant operators and engineers. But for the bad guys, like the potential attackers or adversaries, this is actually their job. They have a lot of investments to do some research. So we assume that bad guys already know this, and we would like to share some information with the good guys so they would be able to act upon this. So let's go to the talk itself. Power plants. Power plants is like the most common way how humans get their power, their electricity. They're everywhere around us, and I believe the closest one to Leipzig is called Lippendorf Power Station. And during this research, when we were preparing an introduction, we were surprised how many information about power plants you can get from the internet. It's not just, for example, a picture of this of the same power station on the Google Maps. It is actually a very is a very good scheme of what you can see on the marketing materials from vendors, because when they sell some system that automate power plant operations, they sometimes start with building construction. And on their websites, you can find schematic pictures of actually which building does what and where you will find some equipment, which versions of equipment are used in these systems. But if you don't have this experience, you can just Google things, and you will find out which systems are used for automation in power plants. For example, for Lippendorf, it's some system that is called Siemens SPPA T2000 and P3000, which is actually have another Siemens system inside called Siemens SPPA T3000. So it's a little bit confusing, and it is, and we are still confused. This is exactly the system that we will focus today. The Siemens SPPA T3000, and again, it could be any other automation system, but it just happened the way that we've seen this system more and more often than others. There is a way how you can actually see all the generation sites throughout the world, thanks to the carbon monitoring communities. This is not just power plants. This is also like nuclear sites, wind generation, solar plants, etc., and etc. They are all here marked by different fuel types of generation. For example, there is a coal and gas power plants marked there. So the topic is really huge, and what we will focus today in our talk is mostly the power plants which work on coal and gas. This is important to mention. The heart of each power plant is actually a turbine. We don't have a picture of a turbine on the slides, but more or less, I think everybody saw it on the airplane. They are very similar, specifically in terms of size and mostly how they work. On different vendors' websites, you can actually find a lot of information where those turbines are used. And this is, for example, the map of the turbines from Siemens. Not all turbines specifically are used in power plants. So they have a lot of different applications like chemical plants, oil and gas, a lot of other things. But if you correlate this information from previous slides, you would be able to identify which systems are used by which power plant. And if you will Google more information, you can actually tell the versions and the generations of the systems that are used on these power plants. This is important because of the vulnerabilities that we will discuss later on the slide. So before we will speak about what is the automation on power plants, we should understand a little bit how they work. So we will go from right to left, and it's very easy. A little notice throughout the talk, we will simplify a lot of things for two reasons. One of them to make it more suitable for the audience, and another thing, we don't really understand everything by ourselves. So the first thing you should get is a fuel. Fuel could be, for example, a coal or a gas, and you will just put this inside the combustion chamber, where you would put it, will set it up on fire, actually, and it will generate a lot of pressure which will go to the turbine, and because of the pressure, the turbine will begin to rotate. The turbine have a shaft which will drive the electricity generator, which is obviously will generate electricity and put it on the power grid. So it is important from now on to understand that when we generate some electricity on the power plant, we put this power not just for example, for this Congress Center or for some city. We put it in a big thing called power grid, where other entities will sell this electricity to different customers. There is also a very interesting point about when we do generate this pressure and the combustion chamber is on fire, we have a lot of excessive heat, and we have two options. One of them is to safely put it in the air with condensing towers. This is option number one. And another option is we can do some form of recuperation. For example, we would take this heat, we will warm water, the water will produce steam, and we will put this steam in the steam turbine and produce additional electricity. This is kind of a optimization of some form. So what is the automation in this process? The automation systems that are used on the power plants are usually called distributed control systems, or DCSs. And everything that I just described actually is automated inside those systems. The vendor of the solution want to simplify all things for the operator, because we don't want like hundreds of people working on the power plant. We just want like maybe dozens of people working there, and they want to simplify the whole process of like, they don't care about where they get this gas or coal, how much they need it. They just should be able to stop the generation process, start it, and they control one main thing, which is called how much power we should produce to the power grid. So like how many megawatts of electricity we should produce. This describes the complexity hidden inside these solutions, because there are a lot of small things happening inside, and we will discuss it a little bit later. As I said, these DCSs, they're not exclusively used on the power plants. There are a lot of other sites that would use the same solutions, the same software and hardware. The DCS is not just like a software that you can install. It's a set of hardware and software. There is input-output models, sensors, etc., and etc. As I said, sometimes they start from building construction, like there is a field, please build us a power station. So it's more complex projects most of the time. There are a lot of vendors that are doing it. As I said, we are focusing in this talk on the Siemens one. Now, just a short description of how simplified things are for operators of this DCS software. So, for example, if we would like to answer the question how we would regulate the output in megawatts of our power plant, we would need to control basically three things. Again, we are oversimplifying here. First of all, you would control how many, this is an example for the gas turbine. So we would need to regulate how many gas we would put inside the combustion chamber. We would control the flame temperature, and we will control the thing that gets air inside the turbine. Basically three things that are controlled by simple PLCs in the whole system, and you would be able, for example, to change 100 megawatts to 150 megawatts based on these settings. So the system itself that we are going to discuss is called Siemens SPPAT 3000, and actually, again, as all other DCS systems from other vendors, this is a typical industrial system. It has all these things called PLCs, RTUs, HMIs, servers, OPC traffic, etc., and etc. The only thing that is different specifically for Siemens SPPAT 3000 is that they have two main things called application server and automation server. That's this software running on these servers is not what you will find on other installations. Despite the fact that there are a lot of, if you would read the manuals for the systems from Siemens, there would be a lot of different networks and highways and a lot of things like Siemens would state that there is no connection between the application network and external networks. In practice and in reality, you will find things like specific sensor network, like monitoring of vibration, foreign objects, and some noises inside the turbine. You will find a demilitarized zone because all in all, all power plant operators, they won't have like on-site maintenance guys, engineers. They would try to do a remote support. They would need to install updates for operating system for their signatures of their antiviruses. They would need to push some OPC traffic, so like information about the generation process outside, either to corporate network or to some regulator, because the whole energy market is regulated and there are different entities who would monitor how many electricity you are generating, or they basically will tell you how many electricity you should generate, because this is how many electricity was sold on the energy market. Basically, the whole talk will be structured like this. We will speak first about application servers, then automation server, and then some summary. It all started with the process called coordinated vulnerability disclosure. We notified Siemens about some issues almost a year ago. And like a month at the beginning of December, Siemens published an advisory. It was not an advisory just with the issues just from us. A lot of other teams also contributed to it. And this year's December doesn't mean that Siemens just released the patches. When this system, SPPAT 3000, is exclusively supported, so the system integrator for the system is Siemens itself. So throughout the year, after we notified them about some security issues, they started to roll out patches and install updates on critical infrastructure they support, and hopefully they did it with all the sensitive issues. There is a lot of things to discuss here. We will skip because we are a little bit in a hurry. Things like not all vulnerabilities are the same, and we use, for example, CVSS here to talk about like how critical the vulnerability is, but it's actually not very applicable to the industrial sites. You should understand what you can do with each vulnerability, how you can impact the process, and we will skip this part. There's actually a kind of a threat model in a white paper that we will release later on, like during January, we will hope. So, application server. Application server is this main resource that you would find in the SPPAT 3000 network. Like if someone will remotely connect to the system, it would end up in application server. If someone wants to start the generation process or to change some values, it would be the application server. If there are other servers that would, for example, try to communicate to the application server, they will actually start their work by downloading their software from application server and then executing it. So the first thing you might notice here is there are a lot of network ports available on this machine. And actually, this is like the first point. There is like a huge attack surface for the adversary to choose, like whether or not he would like to compromise some Siemens software, or it's Windows software, or it's another third party. Huge attack surface starting from the fact that all of the installation of these SPPA systems are kind of different. So depending on the version and on the generation, you can find different Windows versions from, I don't know, 2003 to 2016. Hopefully they're all updated right now. But because the update process for such installations is a hard thing to do. I mean, you should wait for maintenance, and it should be like maybe once in a half a year or once a year. You will always find some window where you can use some remotely exploitable vulnerabilities like Eternal Blue or BlueKeep mentioned on the slide. There's tons of different additional software like old Cygwin that will allow you to do privilege escalation, badly configured Tomcat, and we have here these funny pie charts that show how configuration of different software is aligned with the best practices from CIS benchmarks. Those are basically security configuration hardening guides. The most important thing in the application server is a lot of Java software, and in a minute, Rado will tell you about this. Surprise, surprise, one of the most notable problems in the Siemens SPPAT 3000 is actually passwords. There are three important ranges. The first of them is like what's all the installations before 2014 or maybe 2015. All passwords for all power stations were the same, and you can easily Google them. We will also publish like the full word list in the white paper. After these years, Siemens started to generate the unique passwords for all power plants, but until this year, it was kind of hard to change this password. So you need to be aware of how to do this. You need to know the process. You maybe need to contact your system integrator to do this. Starting up from this December, it would be much easier specifically to change password. So it's in the past, even if you know you have these issues, you were not able to simply change all these things. Along with the passwords, you can find the full diagrams and integrator documentation that can show you how the system is built, how it's operating, specific accounts, etc., and etc. Of course, this was not published by Siemens. Those some power plant operators who thought it would be a good idea to share this information. So as I said, the most important thing of the application server is a bunch of Java applications, and please welcome Rado, who will share the details about this.
Hi everyone. Let's look how SPPI software works on application server. Operator can communicate with system through a thin client and fat client. A thin client acts as Java applet inside Internet Explorer browser and communicate with server through HTTPS. So it can be outside of application network, and its communications can be constrained by firewall. In opposite, in case of fat client, software should be installed on operator machine, and client directly communicates with RMI registry to find services, and after that directly communicates with these RMI services. So fat client should belong to application network. Illustration of SPPA architecture was kindly provided by SPPA through the URL. Not to be messed, let's divide it into spaces. In red zone, the items that process requests from thin client and redirects them to RMI services. And in green zone, there are RMI services which act as network services on dynamic TCP ports. SPPA consists of containers. Each container can encapsulate inside one or more RMI services. All type of containers are represented on illustration, and all of them have self-explanatory names. Before we're going deep inside internals of SPPA, let me introduce some tools which used in this research. First of all JARS files inside SPPA are obfuscated with commercial product, but this security measure can be easily bypassed by public available tool, the obfuscator. Also, sometimes it is useful to see how legit software communicates with system. It helps to understand architecture of system and workflow of clients. In case of SPPA, RMI dissector was written. It represents raw TCP streams in human-readable formats. Inside, it uses method read object from Java SDK. It is known that this method is unsafe to insecure deserialization. So be careful not to be exploited through remote pickup. The first pillar of SPPA is Apache Web Server. According it config folder Orion software config can be accessed by an authorized user. In fact, this folder contains some sensitive information of system. For example, files PC system configuration .xmls and files inside AFC contain startup options and configuration of all containers, either application network or automation network. Also, configuration of Orion web application in Tomcat also can be accessed using this vulnerability. And about Tomcat, there are 3 web applications registered: Remote Diagnostic Viewer, Manager, and Orion. According to configurations of Tomcat at Apache Web Server, Orion servlets can be accessed through HTTPS. And in the file web.xml, the list of all servlets of Orion application, and the list is really huge. So some of these servlets have attractive names for attacker. For example, browser servlet. In fact, it allows unauthorized user directory listing directories of operation system. But in case of exploitation, another servlet is more attractive. File upload servlet allows unauthorized file upload with system rights. Parameters base dir and target may fully control the name of the file. So this vulnerability can be easily transformed to remote code execution. You can override some startup scripts of SPPA or simply inject JSP shell in Topcat web application and get remote code execution with system rights. Also, there are some servlets which contains word service factory in the names. In fact, they redirects HTTP requests to RMI services. Inside, they parse parameters from HTTP request and search desirable RMI service according to parameter service URL, and further invoke call to the public method of security service and the name of the method defined in serialized object in the data section of HTTP request. Also parameters of these calls also defined in this object. So now we have a situation when thin client and fat client can access RMI services. But in case of fat client, it can also directly communicate with RMI registry. So if application server missed some important Java security updates, it contains insecure deserialization vulnerability. And using public tool YOSO serial, we can simply exploit it and get code execution with system rights again. The next task will be to list all available RMI services of SPPI system. At first step, we simply use class locate registry of Java SDK and get a big list of services. All but one are Gmx RMI services. I assume that they perform some general interface for COM, for control and manage containers of SPPI. For further investigation, we only choose lookup service. In fact, this service looks like some collection of another RMI services. Using its public method list, we get the name of all available services, and using the name and public method lookup, we get the reference of RMI service. All RMI services in this step implement interface service factory. So according to this, we can assume that this is again collection of another RMI services, but in fact it doesn't have public method to get the name of the service. So we need to decompile. The class and find some factory methods which create RMI services. For example, create admin script, and inside we can find the name of created service. As it can be guessed, it's admin service. So using public method get service and this name, we finally get the reference to next level RMI service. And in final step, we get the reference to RMI services which perform real job of SPPI. But this RMI service also contains a lot of public methods for unauthorized user. So to sum up, we traverse a registry, and at each level we found a lot of RMI services, and the last item also contains a lot of public methods. So the attack surface of SPPI system is really huge. So now, when we list all available RMI services, the next question is how does authentication of client request performs on the system? To answer this question, let's look how client request to security service processed on system. First of all, client gets the reference to security service using some client ID. Further, PC Service Factory tried to get valid session using this client ID in Session Manager. If Session Manager will fail in his task, the exception will be thrown and client will be failed. But if it succeeds, valid session ID will return to PC Service Factory. And further, in its turn, instance of security service will be created in factory method, and value of session ID will be stored in a login ID inside security service. And finally, client will get the reference to security service. Further, he can call some public method of it, but these methods can perform privilege checks of user using login ID in Security Manager. So to sum up, we have two security measures in this system, but there's a question how user client can perform login operation if he doesn't have any valid client ID. In this case, at startup of the system, session manager will be added anonymous session with client ID equals 0, and client will use this client ID and perform login operation. But attacker can also use this feature and simply bypass first log. So to sum up, there is only one security measure on the system, and it fully delegated to method of RMI services. But amount of RMI services is huge, amount of public methods is really huge, and so it's become really difficult to manage security service of system according to this information. So we know all inputs of system, we know all possible security measures of system, so it's time to find vulnerabilities. In the list of RMI services, there's one which looks attractive. It's admin service. It can be accessed with anonymous session. Inside, it has public method run script. This method doesn't perform any privilege checks, so we can call it without any credentials and so on. At first step, this method creates instance of class loader using bytes from arguments. And in fact, this step will load arbitrary Java class. This class should implement interface admin script and define method execute. And this method execute will be called by run script of RMI services. For this case, we create Java class that simply run OS command from arguments of run script. And we get code execution on system with system rights. Of course, there is more powerful post-exploitation of this vulnerability than simply run OS command. You can, this vulnerability allows inject arbitrary Java class inside running SPPI application. So you can use some Java reflection to patch some variables of system and have influence of on technology properties of SPPI. Also, privilege check inside methods of RMI service can be bypassed with second vulnerability in session service. This service has public method get login sessions. In fact, this method return all session data of all logged users on system. This information includes usernames, IP, and client ID. So if in this amount there is client ID of user that has some admin privileges, attacker can use this client ID to get reference to security service, and this reference will be with some more privileged session. Further, attacker can call public method of security service, get all users, and get all private information about all users of the system. And password hashes also included in this private information. So, to sum up, we have both of these vulnerabilities can be accessed through HTTPS, and firewalls rules can be bypassed. In general, all communication with RMI services are unencrypted, so usernames and password hashes are transferred in plain text. This is more critical for fat client case. Moreover, password hashes doesn't have any session protection mechanism. So if attacker can perform man-in-the-middle attack against some user of SPPI and capture the traffic between this user and application server, he can get valid username and password hash of the system, and simply reuse these credentials and perform login operation on the system. Moreover, he also can change the password of this user. I talk a lot about usernames and password hashes, so it's time to understand how these items are organized on the system. Alex?
Hello everyone, let's continue our discussion about application server. On the previous slide, you can see how remote authentication works. Now, sorry, I repeat. On the previous slide, you could see how remote authentication works, and now I'm going to tell you about how it's organized locally. After the system gets started, it begins to read two files, user1.xml and pdata1.xm, to get user list and their password respectively. The user's one file is a simple XML, while pdata1 has a slightly more difficult structure. It's a gzip archive encoded in base 64. There are Java serialization object in the gzip archive containing a specific XML. The field of the XML present on the slide, they are used to calculate hash value and check password during the authentication. On the bottom of the slide, you can see password check algorithm in a pseudocode. The cryptographic scheme is a typical crypt hashing scheme, like in your Unix and Linux machine. It has a number of iterations, souls, and the only one thing was added is hard-coded soul, which is the same for all users. The tool to extract password hashes and their parameters from the pdata1 file has been developed. On the slide, you can see its output. The tool can be used during the password auditing to check password, to check weak or dictionary password, and their hash calculation parameters. The tool is available at the link below. Draw the line and application server analysis. First, as we have seen, attack surface is really huge and includes a lot of different components. Secondly, it's about remote connections. Whether SPPA has or has no remote connections according to vendors or someone else who told you it, you should check it anyway. And the last thing is attacker has an opportunity to impact power generation process. For example, it can stop generation, change some output value, or gather some additional information about generation process, and all this action can be done from application server. That's all about application server, and let's start discussion about automation. The main goal of the automation server is to execute real-time automation functions and tasks, depending on the power plant project architecture and its features. The role of the automation server can be different. We have distinguished three roles. The first one is automation role. There may be slight confusion because the term is used both for server and for its role. But analyzing automation server configuration and publicly available information, we have found that whatever the role is, almost the same hardware and software are used, and we have decided to use this kind of classifications that seems less confusing to us. At the same time, it's slightly different from the vendor's classification. Anyway, meaning automation role, having automation role means that the server is responsible for interaction with input-output modules which control and monitor power plant equipment such as turbine, electric generator, or some other. The second role is communication. In this role is used for connection the third-party software and system. In other words, it's just a protocol converter supporting such protocols as Modbus, IEC 101, 104, and some other. And the last role is a migration role. This role is used to connect previous version of SPPA T3000 and other legacy systems such as SPPA T2000 or Teleperm ME. Automation role in automation server in automation role can be run on thematic S7 PLC and an industrial PC. Other role can be run only on industrial PC. Now let's talk a little more about each role. And let's start with automation role based on PLC. PLC will directly control field devices like valves in turbine and access to them. And access to them is a game over for any security discussion. They usually represent the lowest level in different reference models, such as Purdue model, for example. Any configuration changes and updates for PLC require to stop technological process. So these devices always have security misconfiguration, firmware without security updates, and unsecure industrial protocols. In case of SPPA, they are S7 protocols, LPC data. There are a lot of information about S7 protocols in the internet, but not so much about PLC data protocol. So we had to deal with it and analyzed ourselves. It's not a special protocol for SPPA. When you program your thematic PLC and need to exchange some data between them in real time, you use this protocol. It's a quite simple protocol, and maybe its description is available somewhere in the internet, but we couldn't find it. So just a case, show you its structure. Anyway, there are no security mechanism in this protocol.